In this video, we're going to talk about the concepts of absolute analysis for general plane motion. This will be our starting point for investigating the general plane motion of a rigid body. We have previously talked about the fixed axis rotation of rigid bodies. In this case, there's translation and also the rotation of a rigid body. In this analysis, we use geometric relations between linear and angular variables of rigid bodies. There can be more than one rigid body indeed, and then that would be called the multi-body analysis. And the differentiation of these relations will provide us with the velocity and acceleration level relations in between these velocities. A good example to this would be a planar robotic system. Let me just draw you a simple 2 degrees of freedom planar robotic system. There is first revolute joint, which is connected to the ground. There is our first link. And then there is another joint here, revolute joint, and then a final link. And we are interested in the velocity and acceleration of this point. Let's call it A. Now, we need to define these rotations, and we can define it with respect to the ground frame, if you like. Let's call this theta 1 angle. And then we can also call this one as theta 2 from the ground. So this is basically parallel. It's not possible to do that, but this line is parallel to the ground frame. And we can call these link lengths as A1 and A2 link lengths. Now, with respect to a frame that will attach at this point, okay, so let's say that we have a frame, XY frame here, X and Y. Now we can write out absolute position of this A point with respect to these angles, right? And this would be in the X direction, so I'm taking a look at the projection of this link onto the X axis. That will be A1 times cosine theta 1, and then it will be plus A2, this is the second length, and then I'm trying to find the projection of that, cosine theta 2. And then y-axis will be written out as A1 sine theta 1 plus A2 sine theta 2. As simple as this. Now I have a relationship between the absolute position of this point A with respect to the origin of this frame. Now if I take the derivatives of these with respect to time, I will receive the information about x dot and y dot, and then another derivation with respect to time will give me the information about x double dot and y double dot of this A point. So this is what this is actually is the A point's location in the xy frame. So that's why I've written it out as x and y, but also you can name this as the vector r O to A in the x direction. And then this could be written out as the r O to A in the y direction. Okay, and O point is the origin of this frame. Now, based on this information, now we had a two-body situation here. We can take a look at the a single body. Now this is a rotating wheel, and then there's this assumption that there's no slip. So kinematic-wise, the linear motion is directly related to the rotational motion if there's no slip, which means that if this rotation started from this initial condition at the O point where the center of the wheel was at O point, then after theta amount of rotation, and the rotation happens around this axis in this direction so that it goes to the left, otherwise it will go to the right if it is rotating in the opposite direction. If it is rotating around this axis, then the amount of angle elapsed is theta, and it is shown over here as theta. Okay? And the arc length is actually equal to s. The arc length that has been covered here is actually equal to s, and therefore we can propose a relation saying that s is equal to r theta to find the arc length. This is the arc length, and s is equal to the arc length since it's moving on that direction. Now, if there was slip, obviously this relation would not be formed. S would be different from r theta due to the amount of slip that it has. But since there's the assumption of no slip motion, we have this direct kinematic relationship S equal to r theta. Now, based on that, we can derive this with respect to time and find the equations as r theta dot, which is omega angular speed, is equal to s dot, and s dot is actually the motion of this rigid body. S dot is equal to v0. So v0 is defined as r omega. S double dot, this is the acceleration of the rigid body, a0. This is dependent on the angular acceleration of this rigid body. But when we are talking about the acceleration and velocity of rigid bodies, be careful that we are talking about the acceleration and the velocity of the mass center. So this center located here at O prime, we are talking about the acceleration and velocity of O prime, because the acceleration and velocity that we're going to find out at different locations of this wheel will be different. Now, in order to find that information, we can do the absolute analysis. For example, a specific point right over here. That point actually started its journey from the location where it was right at the bottom, and then theta amount of angular motion has elapsed. As a result of that, it moved from the bottom to this point, and as the motion will continue, this point's location will change and return back to the bottom. Now, I can directly write out an equation to relate this motion to the absolute location of this point. By absolute location, what I mean is its location measured with respect to inertial frame. And the inertial frame here is the y and x axis located here, and it has this origin right over here. And we can define the location of this point with respect to this origin. So I can find the projection, this projection here, of r times sine theta is this projection. This is in the negative direction. So s minus this value would provide me with the information of the x-axis location of that point in time. So that becomes s minus r sine theta. It goes s forward, and then minus from s we go as r sine theta. This is the projection to the x-axis. We can find the projection of this point onto the y-axis, and that would be, this length is r minus r. Now the projection of this point onto this axis would be r cosine theta. So r minus r cosine theta would be the y-axis. And if you do the necessary calculations for the derivations of these two equations, we'll find these results for x dot, y dot, and then another derivation with respect to time. We'll find the equations for x double dot and y double dot. And this point's velocity, absolute velocity and absolute acceleration, will follow this information for changing theta values. Now, here's the interesting situation. When A is the contact point, that means theta is equal to 0. When theta is equal to 0 and we are investigating this point, what happens? With respect to the velocity equations, when theta is equal to 0, this is 1 minus 1, the velocity in the x direction becomes equal to 0. And sine 0 is 0, so the total velocity of that point, the absolute velocity we're talking about, is equal to 0. How does that happen? Let's take a look at the rigid body again. This rigid body at that instant is moving with a v0 speed. This v0 speed is to the left, okay, and this is equal to r omega. And the rigid body is also rotating with an omega angular speed. That means at this point, this point's relative motion with respect to the mass center is in this direction, and the amount is r omega. So it has r omega minus r omega speed. That means it has a zero speed at point A. So at the point of contact, if you have a wheel which is rolling without slip, its absolute speed is equal to zero. However, it has a relative speed with respect to the mass center, and that's r omega in the opposite direction of motion. In a similar fashion, we can work out the acceleration equations, and for the x acceleration, what we get is 1 minus 1 again, and then we see that there's no acceleration in the x direction. But then in the y direction, we find out that this is equal to 0, but then we have r theta dot squared in the y direction, and this is the centripetal acceleration information, as you remember. Now, why do we have this? This is towards the center at that instant. This is in the y direction. In the y direction, towards the center, we have this acceleration. And the reason for this acceleration is that the velocity direction, the velocity vector's direction is changing at that instant, and therefore we have this acceleration component at that instant. The acceleration of the point of contact is not necessarily equal to 0. There is a component of the acceleration in the normal direction, and because of that, the direction of the velocity vector of that contact point will be changing in the next instant.